So this is a short version, an overview version over my lecture on the basic concepts of for robotic manipulation for robot arms. So we talked about robot vehicles and the mathematics behind that in the first part of the course, and from now on we will be talking about arms, which are sometimes called manipulators, as they often have a attachment that can, connect to objects and lift them and do something with that and so on. Even though I will not really talk about hands and grasping and things like that, we'll just talk about the arm moving what we will call the end effector to some target object. So first point I want to make is that there's sometimes talk about two different levels: the task level at which a robot arm manipulator connects to constraints, and then the control, how you actually actuate the arm. So this first level is the one at which the autonomy plays a big role, at which you have, for instance, vision to perceive objects and segment them from the environment, and you might have to estimate the pose to be able to plan the motion of the end effect of the gripper to then ultimately connect to that object. And that's where, as I mentioned earlier in the course, the demands for autonomous robots on perception are much more demanding, much more challenging than the tasks that arise at the perceptual performance that you need for cars, for vehicles, which do not necessarily have to segment objects and don't necessarily have to estimate pose, and might have many more, might be much more structure in streets and so on. So here we will have all these projects, but I'll not really talk about the perceptual side of that and the scene representation side of it. Just take for granted that we somehow know about the objects. And in fact, most of what I will be talking about is really part of classical non-autonomous control, what I talk about today. So this question of the relationship between these two levels is a topic in kinematics. I'll talk about that in a moment. It is a major topic in understanding human reaching and human manipulation, and in animal movement like that, including actually things like locomotion, where you use your feet to step and so on, and very similar. Could think of walking and putting your foot down somewhere as a form of reaching, because you're putting your foot in a particular location to, for instance, have a safe step at some point. So that problem is very interesting to human movement. You will see that toward the end of the course when we talk more about that. There is called the degree of freedom problem. It's in the notion that you would have task demands on your hand, for instance, where you point, that would be just one 3D pose of your hand, or your orientation as well of the hand. And you would have a lot more degrees of freedom. For instance, very typically, your upper arm as a human has 10 degrees of freedom, 2 at the wrist, 2 at the elbow, 3 at the shoulder, and then the shoulder, this can move in space around like the sternum. That will be 10 degrees of freedom. But you would also possibly even engage the upper body and in your whole body stepping if you manipulate while standing. And so this problem of saying I have demands for the hand and then have to figure out how to use all the degrees of freedom, that's called the degree of freedom problem in motor control. It's a major topic there. It's a little bit of a problem, not to the same extent the problem in robotics. And in nervous systems, it's exacerbated by the fact that we have muscles rather than electrical motors driving the joints, and these muscles can only pull, and so we'll have at least 2 muscles per joint, and typically we have many more. We have multiple muscles converging on joints. So for instance, for the upper extremity, we have on the order of about 40 muscles that act on the various joints that we have up there. And so how to recruit these muscles and which ones and which combinations is a major topic of interest. It's still a topic of research. And my own group actually is working on topics around that. So I'll not go more deeply into that now. So the basic concepts I want to really explain in a tutorial fashion today are, really basic. They are textbook concepts that apply to autonomous robot arms just as much as to conventional industry robot arms. So any textbook on robotics will have these concepts mentioned, and in the exercise sheet that you have, there are references to textbooks that you can use to look up these ideas. So actually, Murray's, Lee, and Sastry is a book I recommend there, and that is a very nice introduction into the fundamental mathematics of rigid body motion. So the different segments of a robot arm are rigid bodies, not deformable. So it is enough to know where one point on an object like that is, and then to know the orientation by attaching a coordinate frame to that body. And in terms of that coordinate frame, you can know the orientation of that rigid body. And if you know that, then you can say where any point on the rigid body is. So that's 6 numbers you need, right? 3 translational numbers. That will be the vector from some base frame that you have attached somewhere to your table on which the robot is mounted. That vector pointing to the point that you have on the rigid body, and then 3 orientation variables that would say how the coordinate frame that is centered on the rigid body is oriented relative to the base frame. I could subtract that vector and then have them both coordinate frames have the same origin, and then you can just talk about the rotation that you need to do to get from one to the other. So that's the fundamental mathematics of rigid body motion. The problem is, it's a very classical issue, like more than 100 years old. And the problem, if you want to say that, is that the representation of rotation is a little less obvious than the one for translation. Translation, straightforward, 3 numbers for the 3 components of the vector. But translation, rotation, there are multiple different frameworks that are complicated by the fact that different rotations around different axes are not commutative. So you really have to keep track of whether the angles you specify are for rotation first around X, then around Y, then around Z, or in some other order. These are the different ways of how Euler angles can be defined. And the rotation matrices have many more entries than just these 3 angles. And they are actually not independent, therefore, and there are various ways of combining these 2 sorts of things. And actually the most advanced way of doing that, that is, for instance, espoused in this book, is to generate different rigid body configurations from a Lie group. So a differential description where you just say how you reach a neighboring configuration by solving, so by having a continuous set of transformations. So that's just mathematically what you do with a rigid body, and then you build a robot from rigid bodies. The different segments are rigid bodies that are connected to each other, and the way they are connected to each other imposes constraints, joint constraints. So the typical industrial robots only have really these 2 types of constraints: revolute joints, which really rotate around one axis, and prismatic joints, when you sort of extend an arm, right? We humans don't have prismatic joints. You can't just grow your elbow. It's fixed. The length of the segments are fixed, but you may know that there are technical devices that are sort of like telescopic arms that extend. Humans, by contrast, have spherical joints, like your shoulder joint, that has 3 directions of rotation, including the inner rotation along the humerus, right? Along the upper arm, you can rotate. And that is not common in robots. So commonly robots do that by chaining 3 revolute joints with different orientations to emulate that. And the robot arm that I flashed previously, like this one here, has a shoulder that here the shoulder is a sequence of 3 revolute joints that then make up this spherical joint. Yeah, and so they are then chained up into kinematic chains. So one rigid body connects to the next, to the next, and next. Here's a minimal kinematic chain of just 2 such joints, and each segment, has then fewer degrees of freedom than if it was an independent rigid body. So, for instance, if you attach a segment to a base frame through a revolute joint, then only movement around that revolute joint remains. All the other, the translation, all other rotations are gone. So you go from 5 to 1 degree of freedom. And along the chain, therefore, you can say that for every rigid body, you have just 1 degree of freedom left if they're all revolute joints. And that's what's to be the case. Okay, so understanding how mathematically characterizing the different configurations of a kinematic chain, and that means for us both just the spatial configuration and its rate of change, its velocity. That's what is called kinematics. In the textbooks, you will see there's a chapter on kinematics, and I'll explain that a little bit now. The other issue is that as a mechanical system, with masses, in particular, with inertial moments when you rotate these things, there are dynamic equations of motion, including the effect of gravity on these arms, that also need to be understood for control, for knowing how the actuators have to overcome forces and so on. And there will be later lecture that will give a brief survey over these kind of problems. And this is sometimes called kinetics, especially in the biomechanical domain. Roboticists, I think, so talk about kinetics or call it dynamics. So we will want to address that now. We'll not just talk about kinematics, just the mathematical description of the different configurations, which serves motion planning. And we will talk about motion planning in another separate lecture, which has the title Timing and Coordination, because it's ultimately about generating time courses of kinematic configurations, and then that time course would be a motion plan, and then the control would be actually bringing about the motion plan by the actuators, and that takes into account the dynamics of the arm. And so this would be, to make it concrete again, kinematic would be, for instance, knowing something about where you want to put your end effector, your hand, robotic hand, and that will be characterizing that desired hand by 3 translational and 3 rotational degrees of freedom. And then you want to figure out what joint configuration that corresponds to. So which of this arm is an anthropomorphic arm, as we say, has 7 degrees of freedom. So when the shoulder is fixed in space, it matches the human. It looks a little bit almost human, perhaps. So an arm we had here at the lab some years ago. And so the task would be to know what kind of joint angles then you're aiming at. And so here I'll just explain that in very simplified terms in the point to the more general description based on this book. So here, this sort of toy example looking at a human arm, really just in 2 dimensions. I'm looking here from the top. This is the human. These are the 2 eyes, right? Looking at the top. It's like a movement here, something in the plane. And in that case, we can write down these equations without any problem. So what we call the forward kinematics is the mathematical description of where the end effector, the hand or robot arm, robot gripper, would be in space given all the joint angles of the kinematic chain. So in 2D, it's very simple there. The upper arm has a joint angle compared to the, let's say, this spatial, the axis that goes across the body is fixed to the body. And then the elbow angle would be the angle between this continuation of the upper arm and the elbow. And so that would be actuated by the elbow, that would be actuated by the shoulder. So 2D is just these 2 variables. And then you can actually figure out where a point, let's say I attached here a pointer that will be attached to the hand, keeping the hand rigid, where a point on that hand is in space. And for that, you need to know the length of the arm segments, the length of the upper arm and of the elbow, L1 and L2. And we consider the horizontal direction X and the forward direction to be Y. So these are the coordinates of the pointer. And then that formula here will give you the position of the hand given the joint angles. You can easily verify that if you want to know where the elbow is in space, then the cosine would be the X component, the sine the other component, and then you want to go from here to that point, and then you can sort of see that you have to add the 2 angles to get the sinus and cosine function. You can verify that yourself. This is, of course, a toy example, both because the joints are only planar and because we're only thinking about a point in space. And more generally, we'll have to think about the orientation of the hand, and that involves, a representation of rotation, which makes it much more mathematically advanced. Very useful is the differential form of this, and we'll come to that in a moment. So here it's trivial. Differential form will be just to take the derivative of this equation. So I want to say the rate of change of the hand position as a function of the rate of change of the joint. So I take the derivative of this, and then that gives me the chain rule. I have to take the derivative of this equation here with respect to all the joint angles and multiply that with the derivative of the joint angles with respect to time. So I end up with this kind of equation. And this derivative of the kinematic model with respect to all the joint angles is called the Jacobian. I wrote it out here explicitly. When you take the derivative of the cosine for the thetas, you get sinus, minus sinus functions. And then, you get two terms here because you have to take the derivative with respect to theta 1 and theta 2. And similarly, for the sinus, you get cosine functions and so on. So the coefficients here in front of these theta dot terms, that will be the different entries into a matrix. I haven't written down the matrix notation. So here it can be seen exactly. And we'll see in a moment why that is a useful thing to think about these velocities. Here, just a hint how that would generalize. So more generally, what you really think about is how a frame at the base, where the base frame, which is attached to somewhere where the robot is mounted on the earth on a table, to a frame that is attached to what roboticists then call the tool, the end effect of the hand. And you're essentially wanting to transform just any vector in the tool frame to just any vector in the base frame. And the two directions, you will know where an object is in the base frame, and you want to have a desired set of how an object should be in the tool frame, for instance, for you to grasp it. And you need to find the configuration that will achieve that, given that the object is somewhere relative, that where the object is relative to your base frame, because you have some camera, you have some coordinates from a plan of the environment. And so this connection between these two frames can be written as a chain of coordinate transform. So you transform the different frames into each other. There are different approaches to do that. The most popular one in robotics is still the Dennevit-Hartenberg one, where you're following the kinematic chain. So you're transforming this to the frame that is attached to the first revolute joint, and then you're doing your rotation, and then you transform this into the coordinate frame that's attached to the next joint, and then you have again the rotation there, and so on. You follow that chain. There's a more elegant approach that uses this Lie group kind of idea, and sometimes called the product of exponentials representation, where you can write the whole thing just as one series of exponentials that it's all matrix valued that are just not executed in particular order. And these exponentials are of particular form of 4x4 matrices. And you can sort of see, get a sense that there's a rotation matrix in here. These three components are a rotation matrix around this third axis in this particular example. And the cosine here minus sinus here across, that's actually the rotation around theta 1, by theta 1 around axis centered here. And then the third component is the translation. And I'm not going to explain that in detail, but that's sort of what it looks like if you do this in the real world. So the inverse kinematics means we're just inverting that original model. So that means that you now want to say, if I know where my end effector is or supposed to be, what are the joint angles? That is the thing that you really need if you give the task to the robots, because typically you will say, I want to have the hand in a particular place, like to grasp an object and so on. So what joint angles should I then try to realize? Right? And these joint angles are the solution of this inverse equation. So in some cases, you can do this exactly. That is, you invert these equations. You can see this involves solving some trigonometric equations. You know x and y. Now you have to find the theta. And to eliminate that, you can imagine you have to get rid of one of those, and then you use an arc tan, arc or arc cosine, and so on. So you deal with all kinds of problems. And that will be no, this is sometimes possible. That gives rise to a problem that is a problem in robotics, but actually not in human movement. Many of these equations will invert harmonic functions, sine and cosine tangent functions, and as you know, these functions are actually not monotonic, so they have often two solutions for almost all cases, except for these singular points where you just touch, but anywhere else. If you say, I know the cosine of an angle, then there are two angles that realize that cosine. And same for sines. And therefore, for instance, for this problem of putting the arm here, there could be two solutions, like this one and the bottom one. You immediately intuit that this is not something you would do as a human, because your joints have joint limits, so you cannot actually realize, if you have this configuration, you cannot actually have the configuration where the arm flips the other way, right? And maybe that's why we have these joint limits, one could speculate. So in robotics, this is actually an issue. So even a robot arm that is not redundant, that has exactly as many joint angles as parameters in the task space it wants to control, still has to select among these solutions. These are sometimes called leaves. For every joint, you might have that. And if you chain that up, that can lead to quite complex structure. And you have to make sure that if you plan a movement, you're not on different leaves. The different leaves actually don't always have the same range of movements. So I'll not explain exactly how that goes, just make you aware that there are some real issues here. So if you look at the differential form, then the inversion of the equation is in a way much simpler. You don't have to do this acrobatics, solving these trigonometric equations. It's a vector valued equation that is linear in the things you're interested in. You're interested in the joint velocity. In fact, that's very typically the case, right? You actually know your current joint configuration at any moment in time. And this tells you what joint velocity do you need to do to realize a certain end effector velocity. So in motion planning, you would say, I make a path for my hand to the target, and at every moment in time, that path creates a velocity of the hand in space, like three-dimensional, also rotational, if you want to control the orientation. And then I can compute what joint velocity vectors I need, and your servo motors mounted on the robot arm can realize those or control these joint velocities. And that's linear in the joint velocities, and therefore you can just do the matrix inversion. So this is the inverse of the Jacobian. Unfortunately, at every moment, every point in the movement path, you have a different joint configuration. So this Jacobian is not a constant. So you have to do this inversion at every moment in time. That can actually be a problem, and you need to, it's computationally, some issues with computation, but it can be done. And so this is a very common way to do that in all commercial robot arms, do something of that nature. That's why the differential form is so nice. It's easy to invert, and it is what you control anyway. You're servoing the velocity. That only works, of course, if the inverse exists, and there are some problems with that are also very commonly problems that roboticists have to address. These have to do with where you are in workspace. So first notion of workspace itself, it's again a toy example in 2D to make it intuitive. If you have a robot arm only in a plane, then you can easily sort of visualize that as you vary the joint angles, only certain locations of your and orientations of your end effector are reachable. Now in 2D, it's very intuitive that the furthest you can get, if you stretch all the joints, that's the furthest, that will be the first you can position in your hand. And in this particular case, if you invert two of those joints, then that's the closest the gripper can get to the origin. So these are the boundaries of the reachable space. If you ask for what is called dexterous space, so you want to still have not just the hand in the location, but also be able to orient it in just about any way, then you get the dexterous space, which is smaller. You can see you extend the wrist, and then you rotate around the wrist to get any end space. It's easier with these robotic joints, which have 360 degrees angular range often, while humans, of course, have the joints limits, which makes it harder to compute these sort of things. So that's one constraint. That's actually a serious constraint. Robot arms are often limited in the workspace. And that means, that if you're working on objects and so on, that it's only a small area in which you can actually present these objects. And what I'm actually driving at is at the singularity. So at which points does the Jacobian become not invertible, which technically means that there's an eigenvalue that becomes as a zero real part. And that typically, that just happen. And so in these simple illustrations in 2D, it shows up essentially at the limits of workspace. So for instance, if it's fully extended, you can see that there's a singularity in that if you give a change in the position of the hand along the radial direction, want to extend it further, that's not going to be possible. So you will just before reaching that, a very small change in end effector velocity will require a lot of change in joint velocity until there is no longer a joint velocity that actually brings it about. And similar here for this inverted posture. And so these are points to avoid in motion planning, because near those you will have real control problems. And so there's a whole of technology in conventional robot arm trajectory planning to stay away from singularities. This just says that. So humans actually do not really have, because of the joint limits, we don't have a lot of these singularities. So like this inverted one, we don't actually have, because we can't do things like that. We do sometimes operate near singularities. For instance, when you stand upright, if you really very stiffly stand upright, then your whole body as a kinematic change is near singularity, because you cannot extend your body vertically. And it can be a little bit of a problem. And in fact, if you do compliant things like playing with a ball, people tend to bend their knees a little bit, maybe crouch a little bit to remain away from that boundary where they are still, they can control very well. And similarly, when you reach, you don't actually do a lot of action with your fully extended arm. You try to operate in a little bit closer to your body. In fact, cooks, for instance, learn to not work all the way extended, to work closer to where they look. Okay, so here a summary of these four things. This is sort of maybe the four things you might really want to understand. So forward kinematic model from theta, knowing where the end effector is, its differential form, where the Jacobian is defined as this matrix. It depends on theta, but not on theta dot. So theta dot is linear here in the equation. And then the inverse model, which would be, from end effector position to joint angle, and its differential form from joint velocity vector to from end effector velocity vector to joint vector. So a brief comment about redundancy. Redundancy is is relative to a task. So for instance, if my task is to only position the fingertip here and I have 3 joints, then that's redundant, because there are 3 variables that I can choose freely, 3 degrees of freedom, but I have only 2 constraints. So if I write down this equation, which is the kinematic equation, there are 3 variables on the right and only 2 on the left. And that leads to the inverse problem no longer being uniquely solvable. So you have multiple, in fact, in many cases, continuously many solutions to the inverse problem. That is, continuously many joint configurations that lead to the same end effector position. You see, if you change the task, for instance, if you ask the human here to dock, that is, have the pointer at a particular location, but also orient pointer in a particular way in 2D, then you have 3 task variables and 3 joints, and that would be not redundant, right? So it is always depends also really on what your task description is. So this is a big topic in human motor control, and I'm someone who works on that, or used to work on that at least. In robotics, when these things are used, the idea is typically to just choose one of those solutions. Among all the possible solutions, you choose one, and typically by adding a constraint. So very popular constraint is what is called the Moore-Penrose pseudo-inverse, which minimizes the joint velocity. So you're doing minimal movement to achieve the velocity of the end effector that you desire, sometimes called also range-space motion. And that's the explicit formula for that. And then you have a solution. There are other inverses that minimize something else, for some physical quantities, some energy or so. This is actually not a perfect solution, because if you do that a lot, as you make different movements, your arm may drift in called the null space. That is reconfigurations of your arm that lead to the same end effector position, but that are different in joint, and that drift can lead to very awkward joint configurations in humans in particular. Because of our joint limits, we couldn't possibly do that. In fact, we empirically found out, this was some of our own work, that humans will make motion that is not in range space, so will not minimize joint velocity. We'll have what we call null space motion, so internal motions when they actually rotate the arm, keeping the hand in invariant. And in fact, we even found that this kind of superfluous, so within that space of non useful movements that don't move the hand, there is more of that in some senses. For instance, more variability across different trials that lies in that space than somewhere else. In robotics, there's always been the notion that these extra degrees of freedom are there to accommodate additional tasks. Like I already mentioned, if you add more tasks to the task level, then the number of degree of freedom necessary increases. So an arm that might seem redundant becomes less redundant if you add another task constraint. So for instance, some old work, we looked at the elbow position in space. There's actually underlying, this is a human arm, and it's a model, pointing with your hand, and then you can actually rotate your elbow around in space, and that rotation could be used, for instance, to avoid obstacles with your elbow, let's say. And there are a lot more kind of models like that. Okay, that's as far as I want to push it here in this summary. So I introduced the degree of freedom problem, to which I now returned here when I talked about redundant kinematics, because there, you notice there is a problem. Characterize mathematically what rigid body motion means, differentiated between kinematics and kinetics, explained kinematic chain, and looked at these 4 aspects of manipulator kinematics: forward kinematics, forward differential form, inverse kinematics, inverse differential form. See you next time.